All right, awesome. Yeah, thank you all for coming. We're going to talk about some cool hardware hacks today. Let's start with myself. Who am I? My name is Thomas Roth, aka Stack Smashing. I'm a security researcher with a lot of focus on hardware and firmware. And I'm also a co-founder at hackstreet.io, where we try to teach hardware hacking and other security stuff. You can find me on Twitter at Ghidra Ninja and also on YouTube. And as always, when you do research, you build on top of others, right? And so there are a ton of people that I need to thank whose work I'm basing this off. And so, for example, Sigusa, Ollie, who built the Thunderbolt patcher, the Asahi Linux team, without whose work this would all not be possible. Carlo Maragno, my partner in crime, and essentially the guy that I just vent to when something doesn't work. Yiska, Fabian, and Caro, Marc Zunier, who built the central scrutinizer, and also the T8012 dev team, who laid a lot of the groundwork for what you're about to see. Now, as always with research, there's a bit of a backstory. And so essentially, the iPhone used to have this proprietary connector called Lightning. And Lightning was nice for some obvious stuff. You could do charging via it. You could transfer your photos via USB. You could do video, audio, all that kind of stuff. What a lot of people don't know is that Lightning also does a lot of cool stuff. So for example, you can do JTAG via Lightning, UART, and also a protocol called SDQ, which controls all of this. And a couple of years ago, I guess like 2 years by now, we created an open source adapter that lets you talk all of these things via Lightning, and we called it the Tamarin cable. And so essentially, it's a small Raspberry Pi Pico firmware. You just solder on a Lightning extension, and then you can play with Lightning and JTAG and all that kind of stuff. Unfortunately, Apple decided to throw all of my work into the garbage because they
USB-C to iPhone 15. It enables charging, transferring data, playing audio and video.
Unfortunately, they didn't list all the cool stuff you could do with Lightning, right? Like, what about JTAG? What about UART? Like, who cares about data? But I mean, if you think about it, USB has a ton of pins, right? Like, there's a ton of pins, and it's likely that you can somehow still get some alternative functionality on one of those pins. And the YouTube comments were harassing me to try this on the iPhone 15 with USB-C. And this got me thinking, like, essentially, the iPhone 15 is not the first Apple device with USB-C, right? The laptops, the iPads, and so on, they've been USB-C for years. And USB-C is a complex beast. Essentially, when you plug in a charger, the USB controller in your MacBook and a chip in your charger, they communicate and they try to determine, OK, what voltage, how much power, and so on can you accept. And this is done over the configuration channel pins on the USB-C connector. And all this communication is handled by a chip in your laptop. It's called the USB-C port controller. And if you open up your MacBook, you can see them nicely very close to all the USB-C ports. Now, microcontrollers run firmware. And so somebody on the old Intel MacBook still managed to dump that firmware by just soldering on a couple of wires, connecting a debugger, and dumping the firmware. This was done by the T8012 dev team. And they didn't just dump the firmware, they also reverse engineered it. And they uncovered that on this port controller, there are a lot of secrets. And so essentially, by using something called VDM, or vendor-defined messages, we can send custom commands to that microcontroller, proprietary commands, and they even reverse engineered the protocol. And so, for example, they found out that we can send the command hex10 to get a list of all actions that microcontroller supports. And those actions are kind of cool because, for example, there's an action with which we can switch some of the sideband use pins to be a serial console. And so suddenly, we can just send a command to the USB-C controller, namely the command 306, and then we get a serial console on USB-C. So that's pretty neat. And on the MacBook itself, that's implemented in the following way. We have the Type-C controller, which we call ACE. That's just a name that's in the firmware everywhere. And there are different versions of ACE. And so, for example, the Intel Macs had an ACE 2, and then the very new Macs, like the M3 Max and the iPhone 15, they have the ACE 3. And there are a lot of connections between the system on a chip and the ACE. There's, for example, USB and Thunderbolt, obviously, for USB data. There's the serial console, but then there's also JTAG. And so on engineering devices, you can actually JTAG the main CPU of the computer via USB-C. And there are a lot more other protocols. And so, for example, on the iPhone, we even found SPMI. On the new Macs, there's some new stuff, and so on and so forth. The problem is, how can we send those VDM messages if we want to play with this? Because essentially, VDM is completely separate from the regular USB communication. And so we can't just use libUSB or whatever. Instead, we need to use special tooling. And some very clever people figured out that the back left port on the MacBook Pro can actually send VDM commands to other MacBooks. And so you can actually debug one MacBook with another. And so they built this tool called MacVDM tool, which is really useful. And also Marc Zenier built a tool called the Central Scrutinizer, which is essentially a hardware adapter that sends those USB commands and allows you to then access the serial console. They use this for kernel development on the MacBook and so on and so forth. Now, we wanted a bit more than just serial. We wanted to be able to bidirectionally talk to the hardware in the iPhone and so on. And so we forked the Central Scrutinizer and built Tamarin-C, which is essentially a bidirectional Apple USB-C protocol explorer. It has a full JTAG probe integrated, and so you can actually speak JTAG without additional tooling. It can dump SPMI, it can talk serial, and all that kind of stuff. And it works both on the new MacBooks and on the iPhone. And so this is how it looks on the iPhone 15. I've got my logic analyzer connected here for debugging for more cables. And so now we can, using Tamarin-C, we can, for example, reset the device and get a serial console. And now you can see on the right-hand side that we get the boot output of the iPhone via serial. And this is all open source, and you can build your own. Or if you convince me, I have a couple of PCBs with me, and I'm happy to give you one. Now, on old MacBooks, all of this was handled by a chip called the ACE2. Now, the ACE2 was essentially a Texas Instruments white-labeled microcontroller, and it has an ARM core. It's connected to the main CPU by I2C, and you can find it on all MacBooks starting with the T2. Now, the ACE2 is proprietary, like it says CD3217 on it, but it's actually a custom version of another Texas Instruments microcontroller, essentially just with a different ROM in it. And so luckily, we can find those data sheets, and there's even some accidentally published material that explains a lot of the commands and so on that you have. But to really understand what's going on, I had to, again, dump the firmware, because I essentially opened up my M1 MacBook, dumped the firmware, and started reverse engineering it. Similar to what TE8012 team did, but on new hardware. And after staring at all of this for a while, I identified the command handler structure. Essentially, we can send commands to the ACE chip, and then it will do certain things. And there are some interesting commands here. So for example, there are commands such as memory read, memory write, memory modify, and so on, that could potentially allow us to get code execution on this chip. Unfortunately, those are locked on a lot of, on all production systems, essentially. And so we can't use them. They are there, but we can't use them. So we need to do other stuff. Now, this communication between the ACE and the system on a chip is on the hardware level, I2C. But on macOS, there's actually an interface called Apple HPM bus, or host port microcontroller bus, that we can use to communicate with the chip. And so this is used by a couple of tools such as HPM diagnose and so on. And the commands that we can send to the ACE are so-called 4CC commands. So essentially, we send a short 4-digit string, and then the chip will do something. And so we actually open sourced a tool for this called ACE tool that allows you to communicate with these chips and so on. The reason I'm telling you this is because we get very important information from this tool, which is the boot status. So we can measure whether the ACE booted successfully, whether it's stuck in bootloader, or whether it's corrupted and went into DFU mode. This will be important later when we try to attack the chip. Now, the chip, as mentioned, has an integrated ROM that it boots from and so on. But it also has an external SPI flash, and the one we can dump. Interestingly, when you have multiple USB-C ports, you also will have multiple ACE chips. And it turns out that they actually boot from each other. And so they're essentially chained together. So only one has a flash, and then it sends its firmware to the others. But the SPI flash does not actually contain the full firmware. Instead, it just contains small patches for the internal ROM. And this makes reverse engineering this firmware terribly annoying. And so, for example, if you have a function call in the disassembly, then that function call goes to another function. That function then retrieves a pointer from RAM that determines whether it's patched or not. And then we actually go to the actual function that we jump to, either in a patched version or in the ROM. And if you have this loaded in Binary Ninja, it essentially breaks all cross-references and so on and so forth. It's terribly annoying. So we also published a couple of scripts to make this easier and fix all of that. But there are thousands of these types of functions. And so it's really, really a pain to work with. Now, this chip is also getting updates in the field. And so if you have an M1 Mac, for example, you can find a tool called USB Firmware Flasher on your device. Unfortunately, these updates are protected using RSA 3072. However, there's one thing here. That signature is only checked during updates. And so there's no actual secure boot. So if you find code execution, you get persistence for free, because you can just patch the external flash, and then you're in. And we indeed found an attack. It's a mix of cool software and hardware. It's abusable if you have root. And it actually survives a full restore. So even if you completely wipe your device, the chip will still be compromised. We have that vulnerability. Apple committed to fixing it in fall, so I'm not going to drop it just yet. But there will be some cool stuff later in the year. However, this is all the ACE2. And ACE2 is on its way out. It doesn't do a whole lot of interesting stuff. And the iPhone 15, which is what everyone is interested in, uses the successor, the ACE3. Now, the ACE3 is, again, from Texas Instruments, but this time there's zero public information. You can't find a chip with the same package. You can't find a chip that looks compatible to this. Instead, it looks like it's either custom or maybe a product that is yet to be released, and so on and so forth. In fact, when I started, you couldn't find a single hit for the labeling on the chip. So yeah. But what's interesting is that on the iPhone 15, this ACE3 chip exists, and it has access to a lot of embedded buses. So for example, SPMI, JTAG, UART, and so on. But some of these are read-only, essentially. And so if we can get code execution on this chip, maybe we can actually start to modify the buses in the system. And so that makes it pretty interesting. It also runs a full USB stack. And so this tiny chip, your USB controller, can itself run a full USB stack. And this makes it pretty interesting, because if you imagine you manage to compromise the ACE3, and you have a checkmate-style attack for the processor, then you could essentially hide it in the ACE3 and get persistence for your jailbreak without actually having persistence on the main SoC. And so it's an interesting target. I know that a couple of people were looking at it, and so that made it interesting to me too. Unfortunately, the ACE3 updated everything that has to do with interacting with the ACE. It doesn't use this USB-C firmware flasher anymore. It has a different upgrade mechanism between the iPhone and the MacBook. And even worse, the updates are personalized and cryptographically signed. But I still had this vulnerability for the ACE2, and so I was really curious whether I could get it to work on the new MacBook. And so I ordered a MacBook M3 Max. I didn't go for the iPhone because the MacBook actually has multiple ACE3, and so you get more ACE for your buck. But the main reason is, in a MacBook, you have much more space. You have debugging pads. You can actually probe. You can solder. It's much easier than fiddling with an iPhone. And you don't need a jailbreak to get started. If you want to do something on the iPhone 15, you first need a jailbreak before you can actually do anything with the ACE. So I did all of this. I ordered it. It arrived. And my vulnerability doesn't work. Damn it. So simple choice. Either I send it back, or as a hardware hacker, you know, open it up. So I decided to open up the MacBook. And once we look inside, we can actually find the ACE chips. One is very nicely located over here. And the other one is over here. Now, you will notice that the debugging connectors that we use on the M1 MacBook are still there. Like these silver pads are unpopulated Molex connectors. And on the Ace 2, these gave us access to JTAG and so on. And so it was obvious we tried to maybe get access to JTAG. Now we have the Ace 3 here. And we again have an external SPI flash. And then, as mentioned, these debug connectors. So I started using a needle probe to probe all of these, see the activity, mapped out the flash pinout and so on. You can all find that online now. Unfortunately, it seems that on the Ace 3, the debug port is disabled. So what do we do instead? We dump the flash. Apple was nicely enough to put the debug headers for the flash nicely exposed on there. And so you can just use a couple of needle probes to get them. Now, I didn't want to solder in this MacBook because I was still in the 30-day Amazon return window. And so, you know, who knows? And so a few dozen attempts later, I had a flash dump of the Ace 3 flash. Unfortunately, this means we have random bytes and it's reversing time. The results were essentially the chip is very different peripheral-wise. Everything has different offsets. As far as I can tell, it just seems to be like these, even the CRC peripheral, as far as I can tell, is at a different address and so on. And so there's not a whole lot that we actually know. Also, it's again just patches. It's again just patches for the embedded firmware. And there were some weird regions with high entropy that look a lot like cryptographic keys, unfortunately. However, I was able to reverse engineer a lot of the firmware headers of the external flash. And one of the things that I found were CRC addresses. Now, I know this was naive, but I thought, hey, I found these CRC. Maybe they don't actually do any secure boot. And so let's try to flip a bit in a $3,000 MacBook. And it doesn't work. I can't get it to boot. I modified the firmware. I fixed all CRCs that I knew of, but it doesn't boot. But at least I didn't fully brick it. You know, I was able to restore it by just flashing it back, so at least it doesn't brick itself once you tamper with it. However, at this point, I don't know, have I just missed another CRC, or is there actual secure boot and so on? So essentially, either I'm bad at reversing, or Apple is good at engineering, or maybe even both. But yeah, what else can we try? Now, I've mentioned before that we have multiple Ace chips in the MacBook. And so one of the things we can do is we can dump all of them and we can compare the differences. And it turns out that they all run different firmware. The back left port has the biggest patch set. And even worse, they all have small updates, and they all have changes to this high entropy area, indicating that we have some kind of secure boot with hashing, signatures, and so on and so forth. Now, one of the things that I was curious about is, can I run the Ace firmware of one Ace on another one? And so I just dumped it, flashed it on the other one, and it doesn't boot. And this is interesting, because if transplanting firmware doesn't work, it indicates that we potentially have personalized firmware per chip. So Apple signs every update for each single chip. So let's continue reversing. Unfortunately, I tried to find a software vulnerability. I tried SWD access. I tried modifying flash contents. I tried fuzzing. And I even found a small timing side channel to find all the commands that the chip implements. But I wasn't lucky. So we have a completely undocumented chip. We have no firmware, and we only have a couple of simple commands that I at least can't get code execution with. Time to give up? Well, I'm a hardware hacker, and I'm really into fault injection. And so let's try to hack the chip via fault injection. And the idea of fault injection is that we introduce faults into the chip. And this can allow us to modify the behavior of the software that is running on the chip. So for example, we might be able to corrupt memory. We might be able to corrupt registers. We might even be able to skip instructions. And there are a lot of different ways to do this. There's voltage fault injection, laser, BBI, electro-magnetic fault injection, and so on. And they all have one thing in common. It's very easy to destroy chips by using them. And so, yeah. I was still in the 30-day return window, though, so just kidding. Mostly. Now, voltage fault injection essentially works by dropping the power supply to the chip for a very short amount of time at just the right point in time and with just the right pulse length. And this can allow us to, again, skip instructions and so on. It's very easy to do, but the problem is that it pretty much requires soldering, right? And so removal of capacitors, it's best performed when you remove a lot of capacitors, but we don't even know what pin is the core voltage. We don't know what capacitor is the actual voltage supply that we are interested in. And it's even more difficult because the voltage rails seem to be shared across a lot of stuff. And so we don't only glitch the A's, we also glitch everything else. But there's this other cool technology that's called electro-magnetic fault injection. The idea is that we create a very high voltage pulse into a small coil, and this lets us inject current in a very precise location directly into the chip. And again, we can skip instructions and so on and so forth. And it doesn't require any preparation. Essentially, we just, point the thing at the chip like this. We zap it, and the chip is hacked. Easy enough. However, the problem is, to do this, we actually need super precise timing because we need to know exactly when in time the check fails. But we don't know anything about the chip. We don't even know what check we are trying to skip, right? Because we don't have the firmware. So what do? We use side channels. And so essentially, my idea was I use a cheap SDR. Normally, you would do this with an oscilloscope, with a very fancy oscilloscope. And so I wanted to do it much cheaper, and so I wanted to use a HackRF SDR. And then we just take a very shitty coil, and we just drop it on the chip, and we capture the magic chip waves. Now, from the computer, using ACE tool, we can actually restart the chip. And when we do that, we can, if we look at the radio spectrum, we can see very clear signals at around 50 megahertz or 48 megahertz. And so, easy idea. We record the spectrum on the HackRF, we reboot the ACE3, and then we look at the EM recording. And then we do some very simple DSP. I mean, it's going to be so simple. And so after 2 days of debugging my signal processing chain, I eventually was left with something that I think looks like it could tell us something. But this could be anything. This could just be the power regulator, but maybe we get lucky and it actually means something. And so we have a nice trace. The problem is for power analysis or overall side channel analysis, we want to take a lot of traces and calculate the averages because then we get like all the noise removed. But each recording was at a slightly different offset. And aligning those is, you can do this in DSP, but first off, I'm not very good at that. And second off, it's just a lot of work. The HackRF, however, has a hardware trigger input. And we can configure that input to essentially start the recording as soon as it gets a rising edge. However, this doesn't actually work in the latest firmware, and so I spent a day just like trying different HackRF firmwares until I could get it to work. And now we just need a trigger signal. And it turns out that if we look at the flash communication of the chip select line will give us the perfect edge just as the chip starts loading our firmware. So we get a perfect timing signal that tells us when our firmware is getting loaded. And then from there, we can offset our glitch and also our measurement, because the firmware will obviously be loaded before the signature check happens. And so hopefully, we can determine when we need to glitch. So easy enough. Start recording on the chip select trigger on HackRF, reboot the ACE3, and we get a perfectly aligned recording. And then your setup looks like this. There's also a trigger inverter off screen because we actually can't use a falling trigger. Now, this is how it looks when you take pictures for Black Hat. This is how it looks when you actually do it in your office. It's a mess. But, it works. We have just a needle probe on the chip select line. We just literally, by gravity, hold the probe in place. Yeah, no soldering. Still in the Amazon return window. Perfect. And then we get perfectly aligned recordings. In fact, they are so perfect that if you look at them in like a visualization, you can see there's a lot of noise on the frequency spectrum, but timing-wise, we are spot on. Now, one thing I noticed is that these peaks at the start, I've seen them before. In fact, they perfectly correlate with the flash activity on the chip. And so we already know that we see something that is related to the activity of the chip. If we are unlucky, we are just measuring the noise of the flash lines. But we'll see. Now, we have this fancy measurement, but how do we use this to actually time our glitch? Well, the idea is easy. We change the flash contents to be invalid. We, again, take a recording, and then we compare the differences. Sounds easy enough. In real life, it means hooking in the needle probes, try flashing until it works, which can easily take an hour. Then you put your EM measurement back, you do the measurement, and you start over because you forgot something. But eventually, you have a measurement of the original firmware and then the modified firmware. And we can see that there's a very clear difference in the spectrum at this point in time. Now, we could try to glitch here. However, we have a couple of more tricks that we can do. Because remember that we found the CRC values. And so if this side channel was working and was telling us something, we can check that by measuring with the original firmware, then only having one of the 3 CRCs correct, then trying with 2 CRCs correct, and unfortunately there's no difference between those two. And then with all 3 CRCs correct, we can see that the signal looks much different and that we actually get the difference in the emissions much, much later in time. And so why not try to glitch here? Maybe that works. And so with that, we have a timing, and next problem is, how do we position the chip shouter? Normally, you would put the chip shouter on a CNC and you would scan the chip. The problem is that just before I did this research, I accidentally got 330 volts on the ground line of my CNC, destroying my computer, my CNC, and everything else connected to it. And so I didn't have a CNC at hand at that point in time. So I just used the biggest probe I had that's as large as the chip and put it on there. If it's stupid and it works, it's not stupid, I guess. And so, yeah, essentially then we have this setup where we have a chip shouter. We have the chip whisperer Husky, which does the triggering and so on. We have the trigger connection and a ground connection so that everything runs at the same potential. And not shown are days of debugging. Again, this picture is bogus. This is how it actually looked on my desk, very messy and constantly stuff falling off the desk. But we are ready to actually attack the chip. And so what do we do first? We just changed the version string. Essentially, from macOS, we can see the version that our ACE is running at. On this was 2.45. And so I just changed that in the flash, flashed that on there, and then we just arm the Husky and the chip shouter. We reboot the ACE3, we wait for the glitch, and then remember how we can check whether the chip booted successfully. We can check whether our glitch was successful depending on whether the chip is stuck in the bootloader, ADFU, or whether it made it through into the app code. And so I built a very simple Jupyter notebook for this that just essentially runs the glitch over and over again. You can see that we get like 1.6 attempts per second. And so this was running for hours. And that's also where the troubles start. Sometimes the ACE completely stops responding, and then we need to auto-reboot the entire MacBook. But if we reboot the MacBook stops charging because we just reflashed the charging controller. And so then you have 8 hours to try to get the attack working. Then you have to restore everything by putting the probes back on, reflashing, rebooting, waiting till the MacBook is charged. And then you start again. But eventually, you get success. And indeed, we managed to change the version string to 42. We glitched the ACE3. Yay. But we can only modify patches, right? And we don't know what these patches patch. We don't know when they are called. And even if we have no input and output, even if we get code execution, how do we get data out of the chip? So we can replace functions. We just don't know what those functions do. And even if we knew what they do, we have no way to get data back to our computer. However, remember that earlier on, there were these commands, memread, memwrite, memmodify, and so on. And these are all these 4cc codes. And we can just search in the patches for these 4cc codes. Unfortunately, there are a lot of them. And so, for example, here you can see there's like disk, UFPF, DFUF, and so on in a single function. However, we also have the ACE2 firmware. And with the ACE2 firmware, we understand the full command handling. We reversed everything already. And luckily enough, there was a very similar function in the ACE2 firmware that told us, OK, this is the USB-W command handler, and we can replace it. But what do we replace it with? Well, we can build a payload, but again, each attempt of debugging that payload takes hours to days to test. And there's zero debug information beyond, well, it doesn't work, you did something wrong. So you better get it right the first time, which obviously I didn't. However, then it occurred to me that I can just use the memory read implementation of the ACE2, and I put it on the ACE3, and essentially replace this USB-W handler with the read function from the ACE2. I reduced it in size a bit, and essentially built a trivial memory reader. And so we can now send a 4-byte address to the chip, and it will return the 4 bytes at that address. So attempt 2, replace USB-W command, again, start glitching, debugging, waiting, recharging, and so on and so forth. But eventually, we got successful. And we changed ACE-tool to be able to send over an address. And so we just execute ACE-tool USB-W with the address 0, and we got this value back. Now, if you reverse that value, you see that it's 20060000. And he already nods, he knows what it is. This is the stack pointer reset value. We can read and write arbitrary memory in the ACE3. Yay. Time to dump the flash. And we can dump 4 bytes at a time. So this took literally hours. In fact, it took so long that the battery ran out, and I had to reflash and do the whole thing again. So yeah, lots of time to dump. But in the end, we have the full dump of the ACE3 ROM and RAM in hand. And that's really awesome, because it means that dumping unknown silicon is essentially possible, right? It's not super difficult. It just takes a lot of persistence. We can get code execution without having the actual full firmware. And we can now start researching the ACE3. In fact, we have already some emulation and so on for it going on, and so on. Now, I also finally got a new CNC, and so I was able to do some new measurements. And on my chips, this area is actually the one that I get the most success with. And with a smaller coil, you actually can get much more precision, and everything is much better if you do it right. We also have some nice chip scans coming soon, so hopefully we can actually see what's going on inside of the chip. If you want to reproduce this, we're actually releasing all the tools that we use to do this. So HPM Explorer, the tool to send custom messages with arguments and so on. ACE Enumerate, the timing side channel, which is pretty useless, to be honest, but it's there because we can now get the firmware. And we are also releasing all the timings and the Jupyter notebook. So I can't give you the firmware because it's not mine, but I can give you all the tools that you need to dump it. With that said, thanks a lot for coming. And if you have questions, feel free to line up at the microphones. And yeah, thank you.